Prim's algorithm is a powerful tool for finding the minimum spanning tree in a weighted connected graph. This algorithm helps identify the optimal ways to connect a set of nodes with minimal total cost, making it a valuable technique in various fields including computer networks, transportation systems, and engineering. In this video, we'll break down Prim's algorithm in simple technical terms and provide a relatable real-life example to help you understand its application and significance. So let's get started with what is Prim's algorithm. Basically, Prim's algorithm is a greedy algorithm used to find the minimum spanning tree of a connected weighted graph. A minimum spanning tree is a subset of the edges of a graph that connects all the vertices together and has a smallest possible sum of edge weights. Prim's algorithm starts with a single vertex and iteratively adds the closest vertex that is not yet a part of minimum spanning tree to the growing tree. So let's take a simple example to understand it. Suppose you want to plan the shortest route for a delivery truck to visit 5 stores in a city. Each store has a unique location and the delivery truck has to visit all stores to deliver the goods. Now the distance between the stores can be represented by a weighted graph where the vertices are the stores and the edges are the distances between them. So let's start with any store as the initial vertex. So let's say we start with the store A. Now calculate the distance between the store A and other stores. Now from store A we can visit store B, C and store D with the distances 10, 15 and 20 respectively. Store E is not reachable from store A. So you will add the closest store that is not yet a part of the minimum spanning tree to the growing tree. Now store B is the closest store. So we'll add it to the minimum spanning tree. Why it is closest? Because its distance is 10, which is less than the 15 and 20. Now from this store B, we can visit store A and store C. Since we have already visited the store A, we only consider the store C, which is 12. So add this closest store that is not yet a part of minimum spanning tree to the growing tree. Now the store C is the closest store. We'll add it to the minimum spanning tree. Now we have 10 plus 12. Now from this store C, we can visit store B and store D. We have already visited store B, so we will consider the distance to store D, which is 18. Now you will add the closest store that is not yet a part of minimum spanning tree to the growing tree. Now here store D is the closest store, we'll add it to the minimum spanning tree. Now from the store D, you can visit store A and store C. We have already visited store A and store C, so we don't need to consider these edges. So final minimum spanning tree includes the following edges, that is AB, A to B, B to C, C to D. That is 10 plus 12 plus 18. That is 40 here. Now this Prim's algorithm continues until all vertices are part of the minimum spanning tree. The final minimum spanning tree will have the smallest possible sum of edge weights while connecting all vertices. Please note that in this example, Prim's algorithm is not the most optimal solution, as there might be other ways to visit all the stores with the smallest total distance, but it guarantees to find the minimum spanning tree in general cases. Then comes the Python code for Prim's algorithm. So let's take a simple Python implementation. This implementation uses a dictionary to represent the weighted graph, where the vertices are the keys and the values are the dictionary containing their adjacent vertices and their weights. So let's assume that the input graph is connected and weighted. So let's create a simple graph to demonstrate this algorithm, and then we will implement it, and you can run this code directly on the Google Colab to see the results. So when you will run this code, you will find the results like this, where the minimum spanning tree will be like this and the minimum weight will be 50 here. Thank you.